So today we're going to build on what we did last time, and we're going to take second derivatives. We took the first derivative because remember, if I take the derivative, it gives me the ability to find the slope at any point on the graph. In other words, it will tell me if the graph is increasing or if the graph is decreasing. But you know what? There are other things that can change on a graph that might be important to know about. Okay? Any contact lens wearers in here? Okay, you will get this maybe better than some other people will. When you put your contact lens in, do you look at it first to make sure when you put it in it's going in the right direction? You know what I mean by that? Because you look at the edges, and if the edges are flared out, do you put it on your eyeball? No. If you do, it hurts, right? Because that means you're trying to put it in backwards. It needs to be curved this way, all right? Here's what you're looking for. If your contact lens is concave down on the edges, you do not want to put it on your eyeball because the direction of the curve is changing. Now, the whole contact lens is moving up, but what's happening on the edges is it's not moving at the same curve that the rest of the contact lens is, right? Okay? And so there is a difference between something being concave up and concave down. Think about if anybody have like a puppy that you put out a bowl for, and you have to be careful what bowl you put the water in because puppies like to play, and if they tip the bowl and flip it over, obviously they've made a mess, right? And that's because if a bowl is sitting the way it's supposed to with water in it, that bowl is concave up. I can put something in it and the bowl will hold it. That's the same thing with your contact lens. If your curve is concave up, then it will hold its shape and keep what's inside. When you flip the bowl over, stuff comes out, right? Because it's concave down. And if a picture to kind of help you recognize what's happening here, I'll put it on this. Let's say let's take this curve, and I'm just going to focus in on this one little section we were looking at. Okay? So if we know this part right here is concave up, here's what I want you to notice about our tangent lines. Right here at the bottom of the curve is where we know that the tangent line has a slope of 0, right? Completely horizontal. But then, watch this tangent line. Oops, and I'm having a hard time getting really close. Would you say that's a pretty steep slope? Is it increasing pretty rapidly? It is. Now, if I move a little further up the curve, it's still increasing. But notice what happens when I get far enough along the curve. To get a tangent line, I switch to the opposite side of the curve. Now, is this still increasing? Is that still a positive slope? But is it as much of a positive slope as we had down here? No. In fact, if I scoot a little further on this curve, it's still a positive slope, but notice it's getting more shallow, okay? Until I get to the very top of the curve where this thing will have a horizontal tangent line and the slope becomes 0. So all along that curve, the slope is changing. What we're going to be able to find with the second derivative is this inflection point. And the inflection point, we're going to abbreviate it as POI, point of inflection, is going to be the place where it's going to stop increasing as rapidly as it was, and it's going to slow down on how quickly it's increasing. In fact, let me give you an example from the business world of why this would be important. Okay, so if a company decides to increase their spending on advertising, it would expect sales to increase. Wouldn't you agree? I mean, why would you pay an advertising company to advertise for you unless you think it's going to bring you more sales? So at first, sales will increase at an increasing rate. In other words, yes, I have an increase in sales. And the more I advertise, the faster my sales are increasing, right? The rate is improving each month, the more that I advertise. Now, do you think there's going to be a point where maybe my sales are increasing, but they don't increase as quickly as they were? I mean, logically, there's going to be a point that I'm still spending the same money on advertising, but I pretty well reached all the people, the new people that I was trying to reach. And so my sales are still increasing, but not by as much, because I have gotten almost everybody that I was targeting, and I maybe get a few more new sales, but nothing like what it was. That is called the point of diminishing returns. I'm still increasing my sales over what they were the month before, but the rate of increase is going down. Now, why would that maybe be important to know if you're a business owner?
Because it would mean it's time to slow down your advertising.
Do you agree with Ashley? I think it means you're at a point that it's time to analyze, do I need to continue to spend this much on advertising? Because eventually, if my rate of increase is slowing down, I'm going to get to the point that I don't have any increase at all anymore in sales. And so that actually then becomes an extra expense for the advertising. It's not helping. Got the idea? So and there you can probably think of some other examples in the business world where that inflection point, the point where something begins to change, but it doesn't mean you've hit a maximum or a minimum. It's just there is a change in the amount of increase or change in the amount of decrease. If you're starting a business, think about that. Would you expect when you start a business that you'd probably be losing money initially? Okay. But hopefully there's going to be a point where you are slowing down the amount of money you're losing until you get to that break even, and then hopefully you'll start increasing. So it works both ways. You can have the point of diminishing returns where your growth begins to slow down. It's still increasing, but it's just not increasing at as fast a rate. But you can also, in that startup interval, have the point where I'm still losing money, but I'm not losing money as quickly as I was the month before. That's a good thing, okay? And that lets you track, are you moving in the right direction? So here's how you test for concavity, which is that second derivative test, which will tell us if we have an inflection point, that place where the curve has a subtle change, all right? We're going to take the second derivative, and we're going to check to see, using a sign analysis, whether things on the left side or the right side are going to be negative or positive values. And that's going to tell us if the rate of increase is slowing down or if the rate of increase is increasing, and so forth. All right, so let's go through a few of these examples, see if this will help. But I want you to see what the graphing strategy is, because we are graphing. We have been doing that. And this is going to tell you step by step, if you're going to have to do a graph start to finish, all the parts you would need. First, you analyze the original function. That's where we look at in behavior, and that's not written on here, but I'm going to add it, because we know in behavior is really important for helping us decide what to do outside those critical points. You probably want to analyze your domain as well. Now, where that's going to be important is if, say, you've got a square root function, because if I've got a square root in my equation, can I ever end up with a negative number under a square root? Would that make sense? I can't take the square root of a negative number working with real numbers. So there may be times that my equation tells me only certain numbers make sense, If I'm talking about sales, obviously, I'm not going to have a negative number of items that I sell. Or I'm not, so I would have to check the context of the problem as well to decide if my domain has some sort of restriction. And we said last time if it's easy to find the x-intercepts, I would do that. Oftentimes it's not that easy to find the x-intercepts. We're going to then take the first derivative and set it equal to what? 0, in order to find those critical values and see if we have any local max or local min values. Then we're going to try to take the second derivative. All right? Now, it may be whatever we end up with, you can't take a second derivative. These, on the examples we'll look at today, I think you will be able to get a second derivative. And then we're going to have a second sign analysis in order to determine if we have any points of inflection and to see where our graph would be concave up or concave down. And then we're going to sketch the graph. Okay, so let's look. And if we're given this function, first thing we're going to practice is just finding the second derivative. So we're not going to go through the whole process. We're just going to practice getting a second derivative. So before I get the second derivative, I'm going to have to find what? First derivative. F prime of x would be equal to what? 12x cubed. Then what? Minus 26x plus 13. And then when I take the derivative of 1, that's just 0. Okay. Second derivative would be what? 36x squared minus what? And is that am I done? Because again, the derivative of a constant would be 0. There's my second derivative. Okay? Let's do one more. This one has a fractional exponent. Let's make sure that won't give us a problem. So f prime of x is going to be what? 10x to the 4th power. Plus, now be careful here, how am I going to differentiate 7x raised to the 12/5 power? I need to do what with the 12/5? Good. So I'm going to write it out this way so I don't get lost. I'm going to take the 12 over 5 times the 7, and then that's going to turn into x to the, what do I get for my new exponent? I've got to do 12 over 5, but do what? Subtract 1. And if I'm subtracting 1 from it, 1 could be written as 5 over 5. Subtracting fractions has to have a common denominator. So I'll think of it as 12 over 5 minus 5 over 5. And since it's plus 16 on the end, I don't have anything that I have to worry about there because the derivative of that is 0. Now, let's clean this up before we try to take the second derivative. So I still have 10x to the 4th for the first term. What do you get if you take 12 over 5 times 7 over 1? Yes, that's 84 over 5 x to the, what's my new exponent? Good, 7/5. Now, see if you can get the second derivative. This will be a little exercise in fractions. Okay, 10x to the 4th, when you differentiate it becomes 40x to the 3rd. All right, now let's make sure we don't get lost on this. How am I going to get my coefficient for the second derivative? I have to multiply what?
84 over 5 times 7 over 5.
Good. 84 over 5 times my exponent of 7 over 5 times x. And what's going to be my new x? Well, I got to subtract 1 again, so I'm going to subtract 5 over 5 from it. Won't that give me 2/5? We okay? All right. Unfortunately, nothing cleans up in multiplying that out. We just have to multiply it. And we should have 40x to the 3rd plus, I think it's 588 over 25 x to the 2/5 power. Okay. Before you get too freaked out, do not expect to see a lot of fractions. We're just practicing in case you run into one. All right, now we are going to do a little more than just find the second derivative on this one because we want to find the x and y coordinates of all inflection points. So the one that I showed you on the board a minute ago, we just identified the x value where the inflection points occurred. That's what we did on our sign analysis for the second derivative. But just like on the maximums and minimums where you have to go back and plug those values into the original, if I want to know where the inflection points are, if my second derivative tells me I've got a point of inflection, I go back and I plug that value into the original to find out what the y value is on that point. Make sense? So let's go all the way through that. We'll add an extra piece to what we've done. So here's our original function. If I'm trying to find inflection points, what am I going to need? First derivative or second? Well, I'm going to have to start with the first derivative, but then will I need the second as well? Yes, I will. So let's get the first derivative. What will it be? 6x squared minus 24x plus 26. Okay, and that's all of the first derivative. And since it didn't ask me about maximums or minimums, I'm ready to just go ahead and look for the second derivative to get inflection points. Yes, ma'am?
When we try to see, like, the derivative.
No, it's from the original function is how you get in behavior. If we were going to have to graph this, we would need to know in behavior. Since this just wants us to see if we have any inflection points, that's why I didn't do that. But yes, you're looking at the original when you get in behavior. Good question. Okay, tell me what my second derivative will be. 12x minus 24. All right, at least it's a nice, clean, easy second derivative. So what do I do with it to look for inflection points? Exactly. 0 would equal 12x minus 24. Add 24 to each side, and if 24 equals 12x, what would x equal? That is what we call a PPOI, possible point of inflection. The reason I'm saying possible point of inflection is we might run this test, and if we don't get a sign change, for instance, if it's positive on the left and positive on the right, it means it's not a point of inflection. It's just, it's the only place where I could have a point of inflection. So now I'm going to test it and find out if it actually is one. So I'm going to draw a number line. What's the value I need to put on it? 2. And then I need to pick test points on either side. What do you want to use on the left? All right, let's use 0. That's an easy one. What do you want to use on the right? Maybe 3 or 4. Doesn't really matter. We'll keep it even. We'll use 0 and 4 as our test points. So remember, I'm plugging into the second derivative. Now, we did not write it in factored form, but we could have, and that would have been 12 times x minus 2, right? And if I look at it in factored form, it's pretty quick and easy to run my test. If I put in 0, 0 minus 2 is what kind of number, positive or negative? Negative. And a negative times a positive is a negative. Now let's put in, I don't know why that looks like it's a negative sign there. That should be positive 1. Oh, no, it's 4. That's what it was. Okay. So 4 is our test number. And if I put in 4 in the parentheses, 4 minus 2 is positive or negative? And a positive times a positive is a positive. Do we have a sign change? That tells me that 2 is a point of inflection. And now I've got to find that ordered pair. So my point of inflection will be 2 comma something. And how do I find the y part? Plug into the original. I've got to find f of 2. So I'm going to let you guys plug that in and see what you get. So tell me what you got for the y value into the original. Ooh, he got negative 86. Did somebody else get that, or did you get something different? I'm looking for 18. Okay? Now, double check when you plug in 2 and you cube it, 2 times 2 times 2 is 8. 8 times 2 is 16. Okay? Minus 12 times 2 squared. 2 squared is 4. So minus 48, and then you're going to have, yeah. So probably a little sign mistake or parentheses is what came into play there. And you have a point of inflection at the ordered pair 2, 18. So if we were going to put this on a graph, we'd want to make sure we identified that as our inflection point and try to get that little change, that little subtle change in the curve there if we can. Next one, we're going to take a function and we're going to find where it's concave up, concave down, and what would be the inflection points. Has it asked us to graph it? So we don't have to have all the other information. This is going to be very similar to the one that we did on the board earlier. Just notice we have a coefficient change. Instead of x to the fourth minus 50 x squared, this is now x to the fourth minus 54 x squared. So let's go through. And in order to find concavity and inflection points, will we need a first derivative or a second derivative? Where does that information come from? Second derivative. Now, you have to get a first derivative to find a second derivative, but we don't have to find maxes and mins. So tell me what my first derivative would be on this function. 4x cubed. Good, minus 108x. And then we'll take the second derivative, because we didn't have to find any of the information from the first. We just had to find it in order to get the second. What's going to be my second derivative? 12x squared minus 108. Now, what am I going to do with the second derivative? Set it equal to 0. And when I set it equal to 0, I probably need to do what on the right side? Factor. That's going to help me find where those critical values would be. Do you happen to have a common factor between 12 and 108? 12. Awesome. Factor out of 12. What goes in parentheses? Oh, and x squared minus 9 is kind of nice because what can we do with it? That factors as what? Excellent. X plus 3 times x minus 3. That was a difference of squares. Now, let's check with our sign analysis since, well, actually, before we go to the sign analysis, we need to finish solving this. And what does that mean that my possible points of inflection are going to be? -3 and +3. Because if I set each of those factors equal to 0, those are going to be the only values that I come up with that could possibly make this equal 0. So now on our sign analysis, which is our test for concavity, we're going to put which values on it? That's right. I'm going to have -3 and I'm going to have a +3. And now I need to pick test points. What's one test point you might want to use?
4 to 0.
Okay. How about -4 to the left of -3, 0 in the middle, +4 to the right? Sounds good to me. And we want to plug these test values into which equation? Second derivative. Very good. So we're going to find f double prime of -4. And again, all we need will be the signs. And since we had a common factor of +12, positive doesn't affect anything, I'm just really needing to see what sign I get when I plug into the parentheses. So if I plug in the first parentheses, -4 plus 3 is going to be how much? That's going to be a negative. And then what happens when I plug in -4 minus 3? That's also a negative. And a negative times a negative is a positive. Now, plug in 0. And if I plug in 0 to the first parentheses, 0 plus 3 is what sign? Positive. 0 minus 3 is, and a positive times a negative is a negative. And then let's plug in +4. And what would 4 plus 3 be? Positive or negative? Positive. And 4 minus 3 would be? So a positive times a positive is a positive. We've got some sign changes. What does that tell us? All right, here's what I'm asking. It tells me something about concavity. If this is positive, what does it mean for this section of the graph? It's concave which way? Good. That is concave up. And a minus sign means it is concave down. Very good. So that's where I'm having changes in concavity, and it means I must have some inflection points. So let's see if you can identify where my inflection points are. It's got to be -3 comma something, and it's got to be at 3 comma something. And how am I going to find those? Plug it into the original. I want you guys to do that. Go back and plug in -3 in the original equation, and then plug in +3. Are you getting kind of, well, let's put it this way. Are you getting a 3-digit number? All right, that's good. You should be getting a 3-digit number. I know it looks really uncomfortable when you get those oddball sounding numbers. Is it positive or is it negative?
Negative.
And so you got a negative what? 405. Excellent. You should get a negative 405 if you plug in a -3. And then is there... Positive 3 is the same because our exponents were positive exponents. It means we're getting back the same thing. So these are going to be where our inflection points occur at -3, comma -405, and at +3, comma -405. This is your part C, part of the question, because it asked you to identify the inflection points. I didn't write down the A and the B part, but we see them here in the sign analysis. If I were to ask you from looking at the sign analysis, where is the graph going to be concave up? Give me the intervals that are concave up. It starts where? Think about your number line. Where does it start being concave up? At -infinity, and it is concave up until you get where? -3. And then where else is it concave up? +3 to +infinity, right? And then it would be concave down in what interval? -3 to +3. All right. We still hanging in there? Let's go to the next page, where we're going to do all the parts. We're going to see if we can identify our end behavior. We're going to find if we have any local maximums, minimums. We're going to see if there are inflection points, determine concavity, where is it increasing and decreasing, and try to sketch the graph. All right? Now, the good news is it's a pretty basic equation. All right? So let's see if we can go through the parts. Now, if we're going to have to do the graphing, what would we want to identify first from the original? Say it one more time. In behavior. So let's do that. If I'm looking at this, can you tell me what's going to be my in behavior? Is it even or odd? It's odd. And is it positive or negative? Positive. So what's it doing on the left side? Down on the left and?
Up on the right. 12.2 seconds.
Hang on a second. Okay. There we go. So down on the left, up on the right. Would this look easy to find any x-intercepts? I don't think so. I can identify the y-intercept though. We did talk about that briefly. Remember, my y-intercept is going to be whatever the constant is here. Because if I plug in 0 for x, when I clean it up, it's going to tell me my y-intercept is at 0, -9. Now that may or may not be helpful for me when I graph. It's probably going to help me make my graph just a little more accurate. So x-intercept I'm not going to worry about, but I can see the y-intercept. What would we want to find next? First derivative. All right, differentiate this for me. Tell me what we get. 6x squared minus 12x plus 12. All right. What do we need to do with this? Look for those partition points or those critical values, the only places where I could have maxes or mins. How are we going to find it? By setting it equal to?
0 and take out a 6.
Excellent. And factor the right side, we can take out a 6. So tell me what's going to be in parentheses. X squared Uh-huh.
And plus 2.
Okay. Is it going to be possible to factor that? Is there a pair of numbers that multiplies to give us positive 2 and adds to give us negative 2? The answer on that is no. Instead, the only way we would find our max and our min is we would have to use the quadratic equation formula. Okay? Now, I'm going to go ahead and show you how to do this. I'm going to tell you I will not give you one like this on the test. So since that does not factor, tell me what is A. You remember the quadratic formula?
1,
A is 1. What is B?
negative
Negative 2. C is 2. As long as that's an x squared, I could use the quadratic. If I don't want to factor, I can always use the quadratic formula. But if it doesn't factor, I would have to use the quadratic formula to find where those critical values are. Now, here's how I'm going to solve it. I'm going to plug into negative b plus or minus the square root of b squared minus 4ac all over 2a. If it's been a while, that's the quadratic equation formula. So, I'm going to put a negative, parentheses where the b is, plus or minus square root of, I'm going to put a parentheses for each of these variables, and then I'm going to plug in. So I'll make sure I don't make any sign mistakes. The b value is negative 2. Do you see why I put the parentheses? Because if I don't, I'm going to be so tempted to just write down negative 2 and think I took care of the negative, but then I'm going to have it wrong. So I've got to put the negative sign and then a parentheses, and inside the parentheses is where the negative 2 goes. My a value is 1, my c value is positive 2, and now I can clean this thing up. So I get negative, negative 2, which turns into what? Positive 2. So I've got a positive 2 plus or minus the square root of. Now I need to clean up what's underneath the radical. If I square negative 2, that gives me what number? 4. And 4 minus 4 times 1 times 2 is, 4 minus 8 is a negative number. Okay, now what is that telling me? What happens if I get a negative underneath the radical sign? Is that a real number? No. And if it's not a real number, we saw one kind of like this when we reviewed at the beginning. What does this tell me? Do I have any maximums or minimums? Okay, I have no max or min. In other words, this thing is either increasing on the whole thing or it's decreasing. I can actually already answer that. What's this one going to be doing? That's because I know the end behavior, okay? So it is increasing on the entire domain. Now, just because it's increasing on the entire domain, do you think that means that I can't have any inflection points? I actually could. We're going to find out if we do. So we're going to need to take the second derivative. And that means I'm going to look right here at what the first derivative is, and I'm going to take the derivative of that. What will that give me? 12x minus 12. And then that last term, when I take the derivative, gives me 0. That I can actually set equal to 0 and come up with a value. What's it going to be? I can factor out a 12, and so that gives me 12 times x minus 1. What's the possible point of inflection that I have? X equals 1 is that possible point of inflection. So I do need to run a sign analysis for that. Okay, here's 1. Give me something to the left.
0.
And something to the right. 2. And I'm going to be plugging that into which function? Second derivative. So I need to find f double prime of 0. And if I go back up here, is that going to be a positive or a negative? It's going to be a negative. And if I plug in positive 2 to the second derivative, That's going to give me what sign? A positive. Do I have a change in concavity? Because the negative sign tells me this section of my graph is what? Concave, which way? Concave down, because that's what the negative sign means. The positive sign tells me it is concave up. Okay, and that means that I have a point of inflection at 1 comma something. How do I find the y value of that point? Plug in 1 to the original. So that means I've got to find f of 1, and my original function was all the way up here, 2x cubed minus 6x squared plus 12x minus 9. Let's plug in 1 and see what you get. Anybody got it?
-1.
-1. Double check and make sure that's what you're getting. Now, I'm going to take all this information and I'm going to try to sketch a graph. Okay, what I know was my end behavior. I had a y-intercept of what? Okay, so I probably should extend this graph. Ooh, that's not what I wanted to do. Let me just make a new one. Let's come over here. You can see I don't play with my little tools as much as I should. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I know it's going to be crossing right there. And I know that it's down on the left, up on the right. The only other point I found, because I had no max or min, was my point of inflection. And what was my inflection point? At 1, -1. So I need to put that on my graph. 1, -1 is my inflection point. And what does that actually mean? What's happening there?
Means it changes.
The concavity changed. So everything to the left of that point was concave which way? Down. And everything to the right of that point was concave up. So here's what we're going to have, is a very subtle this way, and then it just slightly curves as it goes through that point. So everything to the right's concave up, everything, and I should have curved that just a tad more, would be concave down. And that'll give you a little bit of an idea of what you're going to try to do in 12.2.